This is ISCI 2001, Chapter 12, The Universe. There are 4 themes for this lecture: the night sky, origin of stars, star types, and the life cycle of a star. The night sky. Early civilizations used the night sky to plan certain events. Here you can see we have Stonehenge. The pictures on the left are the ones of what we have left today. The picture on the right is just a drawing of what it looked like in its entirety. You can see on the right hand side of the picture that you have the hill stones, which is where the sunlight passed through and hit the altar stone. We are not quite sure what exactly they use Stonehenge for. We know that it definitely lines up with the celestial bodies or the stars, but as far as why, we're still not sure. There's multiple theories for rituals or sacrifices. Some even say it's for UFO activity. So we really don't know why Stonehenge was composed, but what we do know now is that it is a very beautiful area that would be very wonderful to visit and just to kind of see the old magical aspects of it or whatever. But we do know that it definitely has correspondence with our sun and the other stars and constellations in the sky. Light from the stars and planets pass through the Earth's atmosphere, and when this happens, it's called scintillation. And what happens is the stars appear as a point source of light, and each generates its own light, which causes twinkling. At the ground level within the atmosphere, is reflected light from a planet. It does not appear to twinkle. This is a picture of scintillation and how it's explained. Basically, if you look where it says star, as it goes down more towards Earth's atmosphere, you can see that the line starts waving a little bit. And scintillation is basically the rapid variation in the light of a celestial body, like a star, caused by turbulence in the Earth's atmosphere, and it causes the star to appear as though it's twinkling, even though it's really not. It's just as steady as our sun is. But basically, it just the Earth's atmosphere causes some turbulence within it. To determine how far away a star is, the unit of astronomical distance used is called the light year. A light year is the distance that light travels in 1 year. It's about 9.5 times 10 to the 12th kilometers, or 6 times 10 to the 12th miles. What this equals to is, in kilometers, it is exactly 9,460,730,472,580.8 kilometers. In miles, it's roughly about 5,878,625,303,183.61 miles. Quite a large number. The origin of stars. Stars are born from swirling clouds of hydrogen gas in the deep space between other stars. The interstellar clouds are called nebulae. With proper gravitational attraction, the cloud of gas atoms begin to condense to form a protostar, an accumulation of gas that will eventually become a star. Here you can see the nebulae on the left-hand side. It is forming. This is the same nebula at the top, and then another at the bottom, and it's just showing how they are condensing to form a star. You can see the bright point of light in the middle. On the right is just a drawing of, if we were close enough to see it, what it would actually look like, where the protostar is at the middle, your accretion disk is around it, and then the jets coming out of the center. Gravitational attraction pulls the protostar from a cloud with a diameter of trillions of miles down to a dense sphere with a diameter of about 1.6 million miles. So you've got a very, very large cloud with a diameter of trillions of miles, where the sphere is 1.6 million miles, which is still quite large, and it will keep condensing. Over 10 million years of contracting and heating, the temperature and density conditions at the center of the protostar start nuclear fusion reactions, which is basically most of the time it's hydrogen fusing into helium, and that nuclear fusion is what creates the heat and the light. The pressure from hot gases and energy from increasing fusion reactions begin to balance the gravitational attraction over the next 17 million years. A newborn star begins its stable life, which will continue for the next 10 billion years. Our sun is about halfway through its life cycle, so it still has a ways to go. The model of the average star, such as our sun, describes the interior as a set of three shells. You have the core, the radiation zone, and the convection zone. The core is very dense. It's a very super hot region where nuclear fusion reactions occur. Like I said, it's the hydrogen fusing together to make helium. The radiation zone, the reason why it's called that is because this is where radiation occurs. It's less dense. It's more like the density of water. The radiation slowly emits outward. Then you have your convection zone, which is where the density is the lowest. Energy is emitted in the form of visible light, UV radiation, and infrared light. Here are some pictures of those three zones. Of course, you also have the photosphere, the chromosphere, and the transition zone. That's and the corona. We call all of those the atmosphere of the sun. But you can see the core, which is where the nuclear fusion occurs. The radiation zone is the next one out. That's where the radiation slowly emits outward. And then your convection zone, which is where the visible light is created. So those are the three main parts of the sun, and then your atmosphere added on to that: photosphere, chromosphere, transition zone, and the corona. Star types. In 1910, Henry Russell from the United States and Egenar Hertzsprung from Denmark developed a new way to classify stars. We call this the Hertzsprung-Russell diagram, or the HR diagram for short. What this does is it helps us to plot main sequence stars, red giant stars, white dwarf stars, and the Cepheid variable. Our star is very small compared to a lot of other stars. It is a main sequence star, and you're about to see a picture in just a moment to kind of explain the difference in the types of stars. One of the things that's important for you to know is that blue stars are the hottest. Red stars are the coolest. So when you see this diagram coming up, keep in mind that when you see blue, blue is hot. And if you want to, an example to help you remember that is if you start a fire or you have a lighter and you start that lighter, if you look down towards the bottom, it's blue. And then the further up you get, it'll be, the red, the yellow, the white. And the further up you move the flame, the cooler the flame actually is. That blue flame is what can actually do some major serious damage and burn you, whereas the red will still burn you, but the flame is not quite as hot. All right, here you have your HR diagram. If you start at the top left, okay, this is increasing temperature, okay? The darker the blue it gets, the hotter it is. Also, if you want to just look at the y-axis and the x-axis of this, let's look at the x-axis first, which is at the bottom. It says O, B, A, F, G, K, and M. O is, you can look just below the O, and it says 30,000 increasing temperature, and on the far right it says 3,000 decreasing temperature. So it's showing you the further left you go, the hotter you get, the further right you go, the cooler you get. Now if you look at the y-axis, that's the luminosity in solar units. So you have 10 to the negative 5, 10 to the negative 4, 10 to the negative 3, all the way up to where you get to the positives, 10 to the positive 5, 10 to the positive 6. So luminosity is how bright it is. So if you look at the upper left-hand corner where the blue is, you can see that it says M sun up at the top, and that is your hottest, most visible stars. As you come down, you can see we're gonna take the diagonal line down first, and then we'll look at the ones at the top right. As you come down in this diagonal, these are the main sequence stars. Our sun is there. If you find at the bottom 6,000, it's between the F and the G, and you go straight up, you'll see the word sun. and that is our sun. So it's in the main sequence. Now, as its life cycle diminishes, as we get towards the end of the life cycle, it's going to be further down at the bottom in red, where you can see the DX Cancri down there. That's more of stars that are getting towards the end of their life cycle. But this main sequence here, it means that they're middle-aged. They're basically in their prime, I guess you would say. And you can see as it moves down, they're going to get cooler, and they're also going to lose some luminosity. They're going to get duller as they move down that life cycle. Now let's look up at the top where it says supergiants. You have Deneb, you have Rigel, you have Betelgeuse at the top right-hand side, and Antares. Antares is actually one of the closest stars to us. But those supergiants, they are getting towards the end of their life cycle. The bigger stars are, the closer they are to dying out. So it's not, it's not that they're going to shrink. They will eventually shrink and explode, but they're going to get very, very large before their life cycle is over. And this picture is not to scale. The Betelgeuse and Antares stars up at the top right, basically if our sun was that size, it would take up, it would go almost all the way to Jupiter. So all of the inner planets would no longer be in existence. We would be swallowed up by the sun. That's how large they are. The giants just below the supergiants, as they get towards the end of their life cycle, they will get bigger and become supergiants. Keep in mind that you do have the different temperatures, blue being the hottest, red being the coolest in those suns. And then at the bottom you can see white dwarfs, which is Sirius B is one of them. And they also have, you can see there's two different stars listed. The one on the left, Sirius B, is going to be your hottest. The one on the right is going to be cooler, but it's still hotter than our sun because it's white and not yet quite yellow. Basically what happens as suns such as ours get towards the end of their life cycle, after they become supergiants, they'll shrink down into a white dwarf. So basically you bounce around this chart quite a lot. You start at main sequence and you go up to giant, then you go up to supergiant, and then you go down to the bottom to white dwarf. So it's not a logical, for our brain, the way that we think that it would logically happen. It doesn't happen that way. It goes up, up, and then down. Protostar. Gravity pulls the gas of a protostar together, and this is the life cycle of a star. Gravity pulls the gas of a protostar together, and the volume expands, and the time frame for this is about 50 million years. It moves from a protostar to a main sequence star, which is what ours is. They're the more massive stars. They have higher core temperatures and use up hydrogen rapidly as they shine at a higher surface temperature. These are what we call the O-type stars. If you look back on that HR diagram, they live for millions of years. The less massive stars shine at lower surface temperatures. These are M-type stars on the HR diagram, as they use their fuel at a slower rate. These types of stars live for trillions of years. This is another picture of the HR diagram showing you that main sequence, giants, supergiants, and white dwarfs. The red giant stage. This stage begins when most of the hydrogen core has been fused with helium. The less energy is made and the star begins to collapse. And let me say that back in the olden days, people used to believe that our sun was fueled by either coal or wood. This was before, we could actually send light rays out to do different experiments and tests. But they were afraid that the sun would burn up in their lifetime because, as you burn coal or wood, if nothing is replenishing the coal or the wood, it's going to burn out. So, but eventually they figured out that it had to be something more than that. And we were able to find out through the process of elimination that it was definitely not coal or wood that was fueling our sun. But with the when our core does start running low and the hydrogen is no longer able to fuse with that helium as readily, This is when it enters the red giant stage. You can see on the top left it says the sun main sequence current size. That small yellow Earth in the very center is the size it is now. When it starts expanding, you can see that it already passes Mercury. And like I said, as it gets closer to the end of its life cycle, it'll still keep expanding out. But once the sun reaches this stage here, it will be too hot for us on Earth, and we will burn up at this point. Back toward main sequence. As 500 million years as a red giant, the star now has a surface temperature of about 4,000 kelvins. A main sequence star is hotter than that. It's about 6,000 kelvins. And kelvins is just a temperature range. It's like Celsius or Fahrenheit. Kelvin is kind of the universally accepted term that we use whenever we're talking about space and the universe. The radius and brightness decrease at this stage, moving the star back towards a main sequence star. It looks more like the main sequence star. It's really not, because it's at this point it's collapsing. This is your stellar evolution cycle. You have the protostar, it goes into the variables, and then the mid-cycle star. Sometimes it'll go down, if it doesn't have enough fuel, it'll go down into a brown dwarf. If it has enough fuel, it'll go through the main sequence growth and expand, and then eventually it'll go down to the white dwarf. The beginning of the end for a less massive star. This is such as our sun. The core reactions decrease and the star expands. The outer layers of the star begin to pulsate in and out. A violent expansion blows off the outer layers of the star, leaving just the hot core. A circular nebulae called the planetary nebulae is formed, and the nebulae moves from the core, adding to the dust and gases between the stars, eventually forming a white dwarf star. And this is an example. On the left-hand side, you can see that it's actually blowing all the other layers of the sun and the sun's atmosphere out. Of course, this is not our sun. This is a different star in the universe. But what happens is it's only left with a small core left, and that's what you see on the right-hand side, what's left of the white dwarf. Beginning of the end for massive stars. These are stars that are much larger than our sun. A massive star will contract after blowing off its outer shells. The massive star may go through a carbon fusing stage to form iron. At this point, there is no energy source, and it loses its high temperature. The star collapses and then rebounds into a catastrophic explosion that we call a supernova. This is a picture of what we believe a supernova would look like at close range. Basically, it explodes. A supernova produces a brilliant light that lasts for months before it starts to dim. The remains of the compressed star, or the compressed core, rather, have gravitational forces acting on them to collapse the nuclei that form a neutron star. Now, this neutron star is highly magnetic and become a pulsar, which is a strongly magnetized neutron star that emits a uniform series of equally spaced electromagnetic pulses. If the collapse of a star cannot be stopped, the star will form into a black hole. And basically what a black hole is it's where it's an area that has so much gravity that it sucks everything around it into it. We believe that at the very center of our Milky Way galaxy is a black hole, which is one of the reasons why it causes our galaxy to spiral. So black holes have been identified in space, and we know that they're there. What we do not know is what happens if you go into it, other than basically everything, the gravity is so harsh that it pulls everything apart. This is a picture of a neutron star. We don't know what's in the core of it. Like I said, that we believe that it's some type of heavy liquid. We're not really sure what that liquid is composed of. What we do know is it causes a huge magnetic pull. These are pictures. The top left is of the solar flares from our sun, at the bottom right is a picture of when a supernova is about to happen. You can see the disk around. You can see the rays that are coming out of the middle, and it really does resemble a protostar. This is just another picture showing the different paths that the star can go through. You can see that it can end as a nebula, a black dwarf, a black hole. Sometimes they just end as a nova. You also have your neutron star. But just depending on the size of the star when the star is born will determine what type of ending it will have. If it'll be benign and just be a white dwarf, possibly a black dwarf. We really don't have any solid proof that black dwarfs exist. Excuse me. We believe that they're there, but because they are black in the blackness of space, there's no way to actually prove it with the tests that we have now. It's just a hypothesis or a theory that we have. We only did one standard today, but this one standard covered a whole bunch. It was to demonstrate an understanding of the stars, planets, and of the solar system. And of course, we only basically touched on the stars today, and we will get further into the planets in the solar system at a later time. Please do not forget to go to Georgia View and do your discussion. Remember, there are 3 different discussion points that you need to make or questions that you need to ask. Also, please do not forget to take your quiz. Thank you and have a great day.